Today we are going to learn regarding the another antenna, that is log periodic antenna here. So this particular log periodic antenna is structurally arranged in such a way that whatever the impedances that it is having, or whatever the radiation characteristics it is possessing here, that all the things are going to be repeatedly, or can say repeat periodically, as a logarithmic of frequency here. That's why it is called as a log periodic antenna here. Okay, and these kind of an antennas are frequency independent antennas here. Okay, so now how exactly the this one, what you can say that power has been fed here. Okay, so remember here, for this particular log periodic antenna here, as you can see in the screen here. Okay, so this is nothing but here it is arranged in a long non-linear array here. Remember, in which the spacing of the elements as well as their dimensions are always equal here. Okay, and here you can see that it is being arranged in the parallel wire dipoles here. This is one wire, this is second, and this is third, and this is fourth, and this is fifth, and this is sixth, and this is seven. So okay, 7 wires are been arranged here. Okay, those are all parallel to each other, and they are increasing in lengths here successively here. Remember, one after another here. Okay, so this is being successively increasing in length here from the feed point here. This is what is called as feed point here, nothing but here where exactly our power supply will be given here. Okay, so you can see here Ln is there here, Ln plus 1 it has been labeled here. Okay, right. So and the Sn is in this one space here, and here it is Sn1 plus here, and the length here. Okay, from this particular point, that is origin, or can say that from where the power supply has been given, this the distance is Rn here, and the next is Rn plus 1 here. Okay, there are four what you can say that sections or part we can consider here. One is included transmission line, second one is loaded transmission line, third one is active region, or you can say fourth one is reflective region here. Remember here, whenever the length of this particular dipole wire, okay, here we are having the 7 dipole wires here. Okay, which are increasing in successive lengths here. Okay, so if at all the length is equal to this particular lambda by 2 here, then only it is going to be in active region, and it is going to radiate here. Okay, otherwise it will be in the inactive region if L is less than lambda by 2, or if L is greater than lambda by 2, then it will, or it does not radiate any radiations here. Okay, and the point one more you remember here, that is all the dimensions here. Okay, all the dimensions are going to increase in proportion to the distance from the origin here. Okay, so length is going to increase from the origin here. Okay, length of the dipole is going to increase here, and length from the distance is going to increase from the origin here, and also corresponding spaces are also going to increase here. Okay, and remember here the dipole length increases along the antenna such that the alpha, whatever the alpha angle is here, this is called as included angle here. Alpha is nothing but an included angle, will remain constant here, even though there is a increase in the length of the dipole here. Okay, along the antenna here. Okay, but alpha remains constant here, that is included angle here. Now, the lengths and the spacing here are gradually increased here in such a way that, okay, the ratio remains the same here. Lengths and spacing are increased in such a way that the ratio remains same here. That is, think but here, if at all I take the ratio of Rn, okay, Rn divided by, if at all I take this Rn divided by uh, ln you take here, right? Okay, the ratio remains the same here. If at all I take Rn divided by ln plus 1, the ratio remains the same here. Okay, in that sense here. Okay, so now the something called a scaling factor comes into picture here, or you can say that ratio design here. Okay, which is always less than the value 1 here. So that is represented by the parameter called as tau here. Okay, now this tau is nothing but here whatever the ratio, or you can say the Rn divided by Rn plus 1 here, or Ln divided by Ln plus 1 here. This will always remain the constant here, or you can say less than 1. Okay, now if at all we take the ratio of the Sn plus 1 divided by Sn here, That is nothing but here the spacing here, spacing between the two wire dipoles here. Sn is between fourth and the fifth dipole here, and Sn plus 1 is between the fourth and fifth and the sixth dipole here, distance. If at all we take the ratio, spacing ratio, there is nothing but here Ln plus 1 divided by Ln is equal to 1 divided by tau here. Okay, so that is the reverse of this one here. Okay, that is equal to k here. Now these two conditions, whatever we are having here, tau and 1 by tau here, okay, these are helpful in keeping what you can say that ends of the dipole here to lie along the two straight lines here, okay, that meet at one point here. That is nothing but here these two, this is one straight line and this is another straight line here, right? These two are going to meet at one point here. Okay, that is nothing but here alpha here. Okay, these two conditions are responsible for having that alpha to be kept as a constant here, even though there is an increase in the space and the length here. Okay, so now if at all we consider a graph here, this is the graph here which has been plotted, that is the input impedance versus the frequency here, that is a logarithmic frequency here. Now this whatever the behavior is there, no, okay, this is going to be repeated here as and when the frequency is going to increase here. That's why this particular dipole is called as a log periodic dipole here. Okay, when this log periodic dipole is operated at a given frequency here, all the structures are not going to radiate here. As I said here, maximum radiation will be there in the active region here. There is a minimum radiation, you can say, or there will be no radiation in the inactive regions here. Okay, so now active region is the one here which is whose length of the whatever the dipoles we are using is yeah, equivalent to lambda by 2, or you can say that it is having the resonant length here. Remember here, shorter the element, higher the frequency, longer the elements, lower the frequency here. So you can consider at this part will be having the highest frequency and this will be having the lowest frequency, no sorry, middle frequency, or you can say that intermediate frequency. And as and when the length of the wire is going to increase here, okay, the frequency is going to be reduced in here. Okay, now if at all like consider the spacing factor here, spacing factor is nothing but here the space between the two dipoles here, you can consider here. Okay, that is nothing but here your Rn plus 1 minus of Rn divided by 2 Ln here. Okay, so that is Sn divided by 2 Ln plus 1. Now I just wanted to understand regarding the tan alpha by 2 here. Okay, so tan alpha by 2 is nothing but here you can consider the upper part of this particular dipole here, that is the upper part of this you consider here. This is total is alpha here. If you consider only the half part, you can consider as alpha by 2 here. Now tan alpha by 2 is given by, okay, now we can see in this particular figure tan alpha by 2 is given by, okay, this particular length is Ln plus 1 divided by 2. This is Ln divided by 2 here. So if you subtract these two things, you will get this height here. Okay, this height, okay, this particular small height here. Okay, so that is nothing but your opposite here, opposite by whatever the adjacent we are having here, right? That gives us the tan alpha by 2 here. Adjacent is nothing but here yes here. Okay, this is s here. Yes, we wanted to calculate this one, no? Where exactly the spacing factor is, no? Okay, that is nothing but here your sigma here. Sigma we wanted to understand here. That's why we need to take this angle, only this angle only. Tan alpha by 2 is nothing but here this particular part divided by this one here. That is nothing but this is nothing but here. This is Ln plus 1 divided by 2 minus Ln by 2. That is nothing but here our the numerator part here. It is opposite here, and this is adjacent here. Okay, so we know that the this factor here 1 by tau is nothing but here your Ln plus 1 divided by Ln here. Okay, so Ln can be substituted with this particular value here. So if at all I substitute here, so what I'm going to get here is Ln plus 1 into bracket of 1 minus 2 divided by 2s here. You already know that if at all if at all the log periodic antenna is going to generate certain radiation here, then its length should be equal to what here? Lambda by 2. So Ln plus 1 is equal to lambda by 2 here. If at all I substitute this one here, tan alpha by 2 is equal to lambda divided into 1 minus 2 divided by 4s here. Alpha is the fx angle. Scale factor is nothing but here tau here. S divided by lambda is nothing but here spacing. Okay, now if at all in the log periodic antenna or dipole successive dipole spacing. Okay, successive dipole spacing here. That is nothing but here your sigma here. Sigma gives the spacing between the dipoles successively here, and the scale factor, that is nothing but here our tau here. Tau gives the length of the dipoles here. Okay, this pitch angle here. Pitch angle. I wanted to have the equation here. The pitch angle, that is nothing but here the alpha here in terms of whatever the scaling factor and the spacing factor here. Okay, so if at all I wanted to have this, sigma is nothing but here s divided by lambda here. Okay, s is sigma is spacing here between the two lengths of the dipole here, right? Now s divided by lambda you consider here. You know the value of s here. S is nothing but here lambda into 1 minus tau divided by 4 tan alpha by 2 here. You can substitute in this particular equation. Now let us bring that alpha, that is nothing but a pitch angle here, in terms of the spacing factor and the scale factor here. Okay, so I just cross I'll just take the tan alpha 4 sigma here, 1 minus tau divided by 4 sigma here. This is how we can get the sigma, or what you can say that spacing factor uh, and scale factor tau with the help of alpha here. Alpha, if at all I came to know regarding the spacing factor and scaling factor, I can identify the angle here. Okay, or if at all we know the angle here, we can get the spacing factor here. Okay, and this vice versa here. That is the end of the log periodic dipole here. Let us understand regarding some of the what you can say that advantages, or you can say uses concerned with the log periodic antenna here. Okay, these are used in the field of high frequency communication here, where multi-band rotatable and fixed antennas are used for television reception here, best suited for all round monitoring here. Okay, these are the some of the what you can say that uses concerned with the log periodic antenna.